Okay, so hello everyone, good evening. Hope you're doing well. So welcome to my channel named 5 Math, and today we are gonna do fluid revision, and which is part 2. And today we are gonna start with viscosity. So what exactly is viscosity? So as you can see in the background, there are two images. In which there is one image in which there are two fluids. As you can see in the first fluid, this fluid easily flows from this first vessel to the second vessel, and in this image this is much broad and takes much more time to get from this vessel to this vessel. So why is that? That is because both of them have different rho's, meaning different viscosities, and also both of them have different densities. So rho 1 and rho 2 are different densities and they have different viscosity. So you must have heard that viscosity of oil is less than viscosity of water. Also density of oil is less than density of water. So this will make you make an relation between densities and viscosities. Also you might have heard honey is much more dense as well as viscous than water. So let us derive what is viscosity. So for an ideal fluid, in this case an ideal fluid is a fluid which has steady flow and no kind of friction. Well, we can say viscosity as a type of fluid friction. Okay, so we can see that if fluid is flowing, then if we zoom in like very clearly, then we can see different layers of fluid. We can assume these layers to be very thin. Okay, so after that, what we can say? We can say that viscosity is when the fluid layers move against each other. Okay, when these layers move relative to each other, then the internal resisting force tries to stop this relative motion, and this property of fluid is called viscosity. And we can say that viscous force is always and only present in non-ideal fluids which are not ideal. Okay, so from this we can see and say that the viscous force is proportional to area. It is proportional to the relative change in distance or change in velocity, where this is v plus dz, because this is having a velocity v, this is a distance dz. Okay, sorry, v plus dv. So dv is the velocity of this, dv is a slight change in velocity, and this dv plus v is the velocity of the new box. Okay, so now after this we can say that the force of viscosity would be equal to k, which k is a constant, a dv over dz. Okay, and now this k constant is called as eta, which is denoted like n but with longer n. So this is just the formula of viscosity, and as you can see there is no relation with density. Okay, so what are the units of this eta? We can say that eta would be fv over a dv by dz. We can see that this is change in distance. This is force on Newton. This is meter square. And this is meter, so these get cancelled. Velocity is meter per second. So we can say this thing Newton per meter square is nothing but just pressure. So this is Pascal times S. And if we denote its dimensions, m l minus 1 t minus 1. Okay, so after that what we can do, we can say its SI unit is Poisson, where this Pascal times second is Poisson. We can also call this poise. Okay. So let us see a question in which let us assume that on a slope a mass of 20 kg and the angle is 30 degree and there is no friction and there is a layer of oil present between the box and the slope, and here we are gonna assume the density of the oil and the thickness to be T. Okay, and this is moving with a velocity v. Okay, so also this poise is 0.1 times poise. Okay, so now we can say that 20 times 10, which is the value of g, times half is equal to 1 over 10, 0.1 times 2.2 times 10 minus 0 thickness divided by dt or t. From here we can say t is equal to 4 into 10 to the power minus 3 meter or 0.4 centimeter. Okay, so after that let us move to Stokes law. So what is Stokes law? This is just a small or simple form of viscous force when the condition is that it is acting on a spherical body. So let us assume a spherical body. On this spherical body we can see that the fluid or the viscous fluid will be acting like this, of the air or any fluid. So he derived that the force for a sphere would be 6 pi eta rv. Okay, okay. After this, let us talk about terminal velocity. So what is terminal velocity? So terminal velocity is the maximum velocity on which an object moved under the influence of the viscous force of the fluid under the any given force like gravity. So let us assume a container. In this container, oil is filled, and in this oil, a ball of steel is dropped. So we can say it is acting, gravity is acting on it, mg, and we can also see that the viscous force of fluid is also acting on it. So what would be the maximum velocity for this object? So we are gonna assume it to be a sphere for simplicity. So for this sphere, the viscous force will be 6 pi eta rv. Okay, and its mass would be m, its density be rho, and radius be r, and the density of water would be rho, and its density would be sigma. The gravity force would be mg. So from here we are gonna balance the upward and downward force, because the box or the ball is moving with a constant velocity after all of the forces have been applied, and so buoyancy force plus viscous force would be equal to mg, or gravity force, or rho volume times g plus 6 pi eta rv would be equal to mg, because the buoyancy force is the weight of the ball displaced. So by Archimedes principle, and so from here we can say that some things get cancelled and we will be left with, okay, so writing this mgs, so now from here you can say 6 by eta rv is equal to 4 by 3 pi r cube g sigma minus rho, and from here we can see the velocity would be 2 by 9 r square g sigma minus rho divided by eta, and this is the terminal velocity for a sphere falling in liquid. Okay, so after this we have a property of a liquid called surface tension. Okay, and this is caused by two forces. Okay, the two type of forces are cohesive and adhesive. So cohesive forces are the forces which are act in the same type of fluid, because from the co we can say it is common. So for common liquid or same liquid, like force between water and water, or honey, okay, or mercury, and the adhesive force is the force which acts between two different types of liquid, like between water, glass and water, or milk and honey. Okay, so due to this we can say what is the cause of surface tension. So we can see from this figure that in this figure the water droplets are tightly packed, and in this figure they are not so tightly packed. So from here we can see this outer layer has no pushing force, but in this case, this let us look at this drop. So this drop is being pulled in all directions. So because of this, we can see that this ball is in droplet is in equilibrium, but we can see this ball is not in equilibrium. Okay, this force and this force get cancelled, but there are no forces to cancel these forces. So that must mean that there is a net force acting on the ball, which will cause it to get inside water and will get replaced by another ball. So we can see from here that this layer act as a membrane or tight layer, and we can see it as stretched membrane. Okay, so now after this we are gonna study about surface energy, and that also explains this phenomena by work done in making the surface is stored as surface energy. Okay, so the surface tries to minimize its surface area by reducing the surface area, and so the surface area could be reduced by either stretching the top surface downwards or inwards, which causes stretched membrane. And you can see that the minimum surface area is of a sphere. Okay, so because of this surface, if this surface is not present, this would be a full sphere, but due to this surface, this is a half hemisphere. Okay, so water always tries to be in the minimal state. And what about what other things also, like fluids? Okay, so we can now see some examples, like this bug. We can see that this is floating on water due to this surface tension. Let this L be the length of its leg. So from here we know that the surface tension T is equal to F by L, and this is also known as sigma. Okay, so sigma is equal to F by L, or F is equal to sigma L. From here we can see the length should be longer, so a lot of surface tension acts on the bug and it floats because there are four legs which even more L, but in human case the length is very less of the shoe. Okay, so surface energy, so as I've already told you, surface energy is the work done in increasing area of surface per unit area. Okay, so this is the original surface and we have to extend it. Let this be the new surface, and from here we can see this distance is x and the force required to do it is F external. So from here we can say that surface energy would be F external times x divided by L into x, where L is this length, the change in area, plus L into x, because there are two surfaces. The first surface is in the front and the second surface is in the back, on the back. So from here we can see that this F external is nothing but just sigma L, as we have seen in the example. So it would be 2 sigma L x divided by 2 Lx. And now from here we can see surface energy is equal to surface tension, which is also denoted by T, which is also denoted by sigma. Okay, so after this we are gonna discuss about bubbles and drops. So the difference between bubble and drops is that we can see in the bubble it is filled with air, and the drop it is filled with water. So for this we are gonna make a new term named free surface. So what is a free surface? A free surface is the surface which is in contact with water. Oh sorry, air. So in this case we can see this surface is in touch with the air. This thing is all this area is also in touch of the air. In this case this surface is touch with air, but this surface is not touch with air because it is water, not air. So we can see bubble has two fixed surfaces while drops only have one surface. So what can we do with this? So for this we made a new term named excess pressure. So what is excess pressure? So the excess pressure is the excess additional pressure above atmospheric pressure due to the compression due to surface tension. So we can see that this thing tries to shrink, which is protected by the water pressure, but in this case this thing just tries to collapse due due to this layer wants to just minimize its surface area. Okay, so because there is air inside which is a fluid, so fluid is compressible, the air is compressible in this case, so this tries to compress the air, so that is the extra or excess pressure. So due to this there is a pressure inside. Okay, so now we can say that the excess pressure, so the radius of the bubble would be, let's say, r. Okay, so for this r radius bubble, extra increase in surface area would be new area minus old area. So what is the new area? New area is 4 pi squared 4 pi r plus delta r, where delta r is the new radius change in radius, so r plus delta l would be new in radius minus 4 pi r. So we can see it would be 4 pi r square minus 4 pi r square. So this 4 pi r square and this 4 pi r square get cancelled, and we will be left with 4 pi delta r plus, okay, so we can say this to be very small because delta r is very small and delta r square would be much more small. So we are gonna ignore this term like we do in binomial expansion, and we will be left with 8 pi r delta r. Okay, so we can do this for drop also, but in the case of the drop there are two free surfaces, and we can see that due to two free surfaces the answer would be 16 pi r delta r. Okay, okay, so now the increase in area is due to the work done by pressure axis. So we know that work done is force time displacement, or pressure inside minus pressure atmospheric times area times displacement. So we know the area, so inside minus PATM times 4 pi r square delta r, and we know this thing to be surface energy or sigma, because this surface energy is equal to the surface tension, and this surface energy is work done per increase in area. And we also know that the work done, okay, work done over increase in area is equal to sigma. So we know the work done and we know the increase in area. From these two equations we can say that 2 sigma by r is equal to the pressure axis. Okay, so from here we can see that for the bubble 4 it would be double, so 4 sigma IR would be P axis for bubble. So why doesn't bubble blow up? Okay, so because if we take a look at the bubble, we can see that this area and this area is identical, and this pressure is PATM. This is pushing this side, but this same thing is happening towards, so on the other side, so that's why bubble do not blow up, right? So after this we have angle of contact, and this topic or term is used to tell us whether the liquid wets a surface or not. So what does a liquid mean wetting the surface? Like if we take case of the liquid like water, then it is gonna wet the surface glass. So if this is glass and this is water and this is mercury and this is glass. So because this angle with tangent to the drop is less than 90 degrees acute angle, that means this liquid will wet the surface, and the opposite or vice versa for mercury or another liquid like that. Okay, so this angle is called angle of contact, and this also help us to determine the shape of meniscus, which will help us in capillary rise or capillary dip, which is the last topic for our video. Okay, so now what can we do with this? So the thing that we can do with this is that we can determine whether the liquid is gonna rise or dip. So this is just angle of contact, which is a very simple thing. Now let us look at capillary rise or dip. Okay, so if we can see in case of water, the water rises if it is that this tube is very thin. Then we can also see that the mercury does the opposite thing. Okay, so we know that the pressure is opposite. So like in this case it is a capillary rise because water has risen above its original level, while this is capillary dip, we can easily see. So now let us derive the height. Okay, so we let us just make some points. Make this point. Okay, this point B, this point C, this point D. So you know that the pressure at B is equal to atmospheric pressure. Okay, and we know that P at C is equal to P of B because of same height, and also because we can make a path through the water between them. Okay, so from here we can see if we want to go to C to V, we need to just decrease pressure. So P of C minus rho GH plus 2 sigma by r, the excess pressure of the bubble, okay, is equal to p atm. Okay, so from here we can see that this p atm and this p atm will get cancelled because p of c is equal to p atm, because p of c is equal to p of v. Okay, so from here we can see that height is equal to 2 sigma over rho gr, height or depth. Okay, so in this case this rho gr, capital R, is small r. Okay, so from here we can see small r is equal to capital R cos theta, or its cos component from the figure. So now we have made it in terms of capital R, radius of bubble, this bubble radius. Okay, but we know that we know this thing. Okay, so its cos component would be the small r. Okay, and now we know this small r too. Okay, so now from here we can see this angle is also equal to theta, and with this we can see small r is equal to capital R cos theta, and we have capital R equal to small r over cos theta. We can just substitute in that equation and we will have equal to 2 sigma cos theta over rho gr, and which is our formula where r is the radius of the tube. Okay, so thanks for watching. See you soon in next video. Till then, stay tuned and don't forget to watch the part 1 of fluids if you have not watched. Bye bye.